Hello, guys. In this lecture, we're going to continue our discussion of AC circuits. So I'm going to just review the basic concepts that we just studied last lecture. So we started, last lecture at the end by mentioning some steps and tips on how to solve like AC circuits. So we mentioned that firstly, like we can use, any method that we learned before in DC in AC domain. Okay, like for example, you can use mesh, you can use like nodal, Thevenin, and so on. Okay, and we said like when you see like a capacitor or inductor, just replace it with its impedance, which is just the same concept of resistance. Okay, and that will make it like very similar to our DC circuits that we studied before. This is of course very good news, but we had some bad news that we use complex numbers because we have like sinusoidal form, and we use like the polar form or the complex form to represent that because it's easy to analyze in that way. But dealing with complex number calculations is error prone, and some can cause like, and also time consuming. But we have another piece of good news that we will not, do that in our hand, although we learned how to do it as I taught you last lecture. But we're gonna use like some online free calculators that do like complex numbers calculations for us. Okay. So I'm just gonna remind you again with this website. The first one here is used for doing any sort of calculation, complex number calculation, like addition, subtraction, division, multiplication. Okay. And the second one here is used to convert from a polar form to rectangular form and vice versa. Okay. And of course, we will not forget our basic, all the time, tool, which is our online calculator tool, the Desmos, and we're gonna use it, in AC as well. Okay, let's start by an example, and this example is simple. I'm gonna solve it, using Ohm's law, which is a very basic concept we learn in all circuits so far. Okay. And I'm gonna give you like a homework to redo this, exercise or example, but using nodal or mesh analysis. And of course, you should get the same answer. Okay, so let's review what Ohm's law say. Ohm's law says that I, the current equal to V over R, right? No, this is some specific form for DC. Here, we use a general form that I equal to V over Z, and Z is the impedance. Z can be a form of resistance, in combination for some capacitance and inductance. Very general, And small letters, as we learned it, is for AC. Okay, good. So in this circuit, it asks us to find the current I flowing in that branch. This is I. Okay. So, and we're gonna do it using, Ohm's law. So in Ohm's law, we should have like one impedance on the resistor, and one source, right? We have a source here. This is our source. Okay. So we need to simplify all these impedances into just one impedance. So let's do the circuit in that way. So we have three branches. We're gonna start by the rightmost branch. We're gonna replace everything in it with a box, and we're gonna call this box Z2. It's the second branch. Then the middle branch, which has like a capacitor, we're gonna replace the capacitor with another box, and we call this box Z1. Okay. Then we put our source, which we're gonna call like V. Okay. And this is I. Good. Now, these are two impedances in parallel, and what we do with DC can be done also in AC here. So we can like simplify Z1 and Z2 into just one impedance. Let's call it Z, and Z, this will be like the parallel combination of Z1 and Z2. So this can be reduced further to such, shape here, or such circuit. One source called V, AC source, and an impedance called Z. And what is Z? Z is equal to Z1 parallel with Z2. Good. Okay, so looks like if we know V and Z, we can determine the current, which is what's required in that question. So what is V? V is simple. V is actually given here. So the amplitude is 120 and the phase or the shift is 60. So it's basically 120, which is the RMS value, angle 60. This is what we learned last time, that we express the sinusoidal like function into like polar form like this, or a complex form like this. Okay? Okay. So V is known. Now what is Z? Z is equal to Z1 parallel with Z2. So we must find Z1 and Z2 to find Z. So let's start by Z1. Z1 is actually the impedance of the capacitor. So we learned that the impedance is minus J of the capacitor divided by omega C. So C is known. So this is equal to minus J divided by omega is 2 by F, and F is known. It's given here, it's 60 hertz. Basically, this is basically the standard electricity that you have at your home. 120 RMS and the frequency 60 hertz. So omega is known. And what is the capacitance? C, it is 50 micros. So 50 multiplied by 10 to the power of minus 6. So we can rewrite this as minus J, 10 to the power of 6, because this minus 6 in the numerator can go as a 6 in the numerator over 2 by FC. So let's calculate that. So we can go to our online calculator here. Let's put it on the side. So we have 10 to the power of 6. Very simple to do here. Divided by 2 pi. So 2 multiplied by pi, and pi is pi. Just write pi, it will convert automatically to the pi. F is 60, and C is like 50. So this will be minus J 53.052. Let's do J2 here. G2, sorry, Z2. Z2 is actually a series combination of a resistor and an inductor. So it's equal to R plus the impedance of the inductor, which is J omega L. Okay, the resistor is 20 ohm, and omega again 2 by F. F is known, and L is 100 millihenry. So 100 multiplied by 10 to the power of minus 3, because we have to convert from milli to like normal henries. Okay, so again we use our Desmos. So salvage what we did before, so 2 by F already known, and we're gonna multiply this by 100 multiplied by 10 to the power of minus 3. It's just 10 to the power of minus 1, which is 0.1. Good, I'm sorry, I'm writing in the wrong location here. So 0.1. So Z2 is equal to 20 plus J 37.7. Okay, that's very nice. Now we have V, we have Z1, we have Z2. So let's write I equal to, I'm sorry, we still don't know J. Yeah. So Z is equal to Z1 parallel with Z2. Okay. As we did in DC circuits, this will be Z1 multiplied by Z2 over Z1 plus Z2. And now it's time for our first use of our free online complex number calculator. So we go to this website here. It's very simple. This is the website. Okay. Of course, I already did some of the calculations there. So I'm gonna remove all of that and just rewrote them from the beginning to teach you. So Z1 is minus J 53.052 multiplied by 20, which is plus J 37.7. And then we're gonna divide by the addition. So just don't write them again, just take them, copy, and then paste, and change the multiplication to addition. And in one click, my friend, you're gonna get the answer. One click, very powerful, very accurate. So, and actually the answer is two ways, like in rectangular form and also in, the polar form. So I'm gonna use the polar form. And why? Somebody knows the answer why? Just look at the equations we have. Yes, it is because of this equation. Because at the end of the day, we're gonna divide v by z. And as we learned in the last lecture, the polar form is very, very powerful or very easy to deal with when you have like a division or multiplication. And the rectangular form is good and easy to work with when you have like addition or subtraction. So that's why I'm gonna use here the polar form. So in the polar form, it's 89.7, you can say 99.8 actually, angle 9.33. Good. Now I is equal to V divided by Z, and V is 120 angle 60, and Z is 89.8, just 9.33. And as we learned, when you divide the two complex numbers together, you just divide the amplitudes. So 120 over 89.8, and the angle will be the subtraction of the angle. So 60 minus 9.33. So I equal to, let's do this in Desmos. So we have here 120 divided by 89.9, 1.33, and this angle will be like 50 something. So 60 minus 9.3, it is, yes, 50.67. Okay, guys, that was it for this simple example. You have to do it like in mesh analysis or node analysis, and you have to get the same answer. Thank you very much for watching this video, and see you in another one. Bye bye.